So I'm here to talk about accelerating your SoC by using more third-party IP, and some of the themes that Tony picked up you'll also see in mine, more subsystems, more focus on software, faster prototyping, reducing verification, and so forth. I'm going to talk in this presentation that there is a bifurcation, some people might even argue a trifurcation happening in the market right now, where the leading edge people are continuing to race to FinFET, but yet the IoT and automotive and many other application segments are increasingly driving a focus on the established nodes and innovation in the established nodes. And then 28 nanometer as the last planar process is going to be around and with us for quite a long period of time right now. But I wanted to start with saying that by no stretch of the imagination is the race to advanced technology in FinFET dead. 6 months ago, some analysts were in the industry were saying, can anyone afford to do FinFET? And the answer is absolutely positively yes. And we're seeing our leading edge customers move there very, very rapidly. I'm going to just start up with this chart, which talks about the time to the first 500 tape outs on the y-axis, and on the x-axis is calendar time. And it's very, very interesting here. Synopsys tracks this, and as you know, Synopsys tools are used in essentially every design being done. So we have a very good understanding of the number of design starts that are happening, and we track in any given process node the time to the first 500. So you can see the total bar here, and I'm just using this as an example. This goes back to 90 nanometers a number of years ago in 2003, and you can see that the time to the first 500 nodes occurred right around Q3 of 2005. And then the lighter color bar in this chart is the production tape out. So the first is the design starts, the second is the production tape outs. So you can see that this regular heartbeat in the industry, which has been pretty much every 2 years, we've moved on to the next generation, has really occurred. You can see from this chart shows the time from 90 to 65. If you look at the peaks and the ramp up, very, very similar. Same thing here at 65 nanometer. Again, a heartbeat of about a couple of years. You remember that 40 nanometer actually took a little bit of time to get to market, but clearly that's well-established node. And 28 nanometer is a very, very mature node by this technology. But what's interesting here is that the next generation is coming online. If you study this here, we're in the process of tracking the time to the first 500 very advanced nodes. And if you look at the lighter color bar here, the orange color bar, you can see that that's the ramping of the FinFET nodes. And if you compare that ramp to the previous nodes that I animated on this chart, you can very much see that FinFET is right on that same relentless 2 years pace that we've seen again and again and again. And what's interesting here is we've chosen to include 20/22 nanometer on this chart too, which is the yellow bar. You can see that, like many people think, like what we're seeing, that 20/22 nanometer process is a pretty short-lived node. We can see it kind of, tightening up there, but we see that the growth in FinFET is very, very real. So that was 16/14. We're actually tracking a large number of 10 nanometer FinFET designs right now. You can see those things just starting to ramp. And in fact, you can even starting to see some tape outs at 10 nanometer with some of the most advanced, primarily IP tape outs or early test structures, but still you're starting to see some of the tape outs. Even a 10 nanometer node ramp, because the industry is really doubling down at 10 nanometer. So I talked about earlier that the world is really bifurcating. You might even say it's trifurcating, but the leading edge is still charging, as I just noticed, as I just pointed out, to 16/14/10 nanometer. But yet there's a big focus on established nodes too, and a lot of innovation that are going on now with RF, with embedded flash, and with MEMS technology coming in to make to make the established nodes, get them a real resurgence, really. We're seeing a very, very nice uptick. And this is, I think, the tale of two worlds and the reasons why you need to have such a difference in your processing technology. On the right-hand side is your high-end application processor, which is racing to 10 nanometer as we speak, multi-CPUs, multi-GPUs, a lot of interface IP, so on and so forth. And on the left-hand side, though, you see a typical example of a block diagram for a wearable application, and it's a much different block diagram, much more focused on low power, much more focused on low cost, and that's requiring unique processes. So, double-clicking here on FinFET a little bit, there are tremendous advantages of FinFET, and that's why the world is going to FinFET, why it's going to continue to go to FinFET. So first of all, the scaling is there for FinFET. If you go from 16 nanometer to 10 nanometer, you're seeing, again, more than doubling in density. You're seeing a nice improvement in power. But what you're really seeing in FinFET, what it really brings to bear is some new electrical characteristics that allow you to really dramatically improve either your power or your performance by 35 to 50%, depending on what you're trying to optimize for. So you're seeing the density in FinFET continue to happen, doubling every node. But more importantly, in my mind, you're seeing some breakthrough power performance benefits from the FinFET technology. And you're also able to see FinFET technology operate at very, very low voltages. We have test chips at Synopsys that are running at 0.5 volts and across full margin, full PVT, production class silicon at FinFET. So you're going to see a whole new wave of very interesting power performance trade-offs enabled by FinFET. But, FinFET also has a number of issues with it. Number one, it's more expensive to manufacture. This actually turns out to be more of a case for litho than it is with the FinFET technology itself. So it's really more to do about double, tripling, and even in 10 nanometers, some quadruple patterning of the litho versus the intrinsic complexity of FinFET transistors itself. One of the big issues with FinFET, and I'll talk about it a little bit more, is that now the transistors are, of course, discrete. So you get quantized lengths and widths, and that has a very fundamental impact on how you design IP. I'll talk about that a little bit more. Some tried and true techniques like body biasing that we've used for generations are no longer quite valid in FinFET. I'll talk a little bit about that. And also FinFET offers some unique challenges in terms of potential heat management because, of course, in the world of planar, everything is connected to the substrate, which is a very nice heat sink. But now when you're starting to build these transistors vertically, getting heat out and managing heat can be a challenge. We're also seeing new yield mechanisms yield loss that needs to be managed, things like fin-to-fin bridging and so forth, where you really need to make sure that your design techniques comprehend those new yield loss mechanisms. But the good news for our SoC designers, our end customers in the world of semiconductors and systems, is that a lot of the burden of designing with FinFET actually falls on the IP provider. And so it's a hard job for the IP provider, but we can actually abstract away a lot of the complexity of FinFET from the SoC designers. So the libraries and tools really kind of abstract away that complexity. But for our IP designers, as I'll show you on the next slide or two, life is continuing to be very challenging, and the investment required to really be successful in developing FinFET IP is actually going up very, very substantially. And of course, the foundries are in the same boat here with us as IP provider, where they have to abstract the complexity of the technology, and they are doing that as well. So let me talk about some of the impact of on IP designers of designing with FinFET. So first of all, let's talk about libraries, logic libraries, which is a good example of this. So as I mentioned before with FinFET, you now have quantized widths, and frankly, more importantly, you have quantized lengths. So as a transistor designer in the past, you could have effectively an infinitely variable channel length. Now you have discrete widths and discrete lengths. And there are clearly ways to get around this by doing things like stacking the transistors, but that is expensive from an area perspective. So you have to really think about what we're finding as an IP provider is that you really need to come up with new, unique, and innovative architectures, the same architectures that you can use in planar devices and nodes past really need to be completely redesigned, we're finding, from the ground up to take advantage of FinFET technology, but more importantly, to get away from some of these challenges in FinFET. You may have heard of something called the lonely FinFET. The lonely FinFET is something that the fab has largely fixed with things like C-PODI and PODI rules. But if a P transistor is just isolated by itself in, let's say, a custom cell, it can dramatically degrade the performance of that transistor by as much as 10 or 15%. And so there's all sorts of rules here about, coming up with dummy poly to manage that effect. But there are a lot of these new design techniques that are coming in as a result of FinFET technologies that you really have to take care of. So potentially self-heating, like I said, you have these vertical fins, and depending on how they're isolated and how they're connected, and the density of them, you can start to see a lot of heat being concentrated in the fins, and therefore really having a pretty significant impact on yield and failure mechanisms that need to be taken into account when you're designing FinFET. In terms of SRAMs, you need a whole new class of read-write assist circuitry to be able to deal with ultra-low voltages. And so what we're finding is that there are dramatic differences when designing SRAMs, in FinFET technologies compared to any previous technologies. The beta ratios or the alpha ratios, which are really just critical for noise rejection and noise immunity. It's the ratio of the pass gates to the pull down or pull up transistors. Again, in FinFET, everything is quantized. So before, if you could have a ratio of 1.1 or 1.2 and really set the design to reject noise, here with FinFETs, you have to do other unique and different techniques to be able to deal with this. There are also, static margin as you're bringing down the voltage to 0.9 volts. I mentioned earlier that we're seeing, successful silicon running at 0.5 volts or less over full PVT characteristics. So as you're starting to see that, you have to have an extremely robust design in terms of your noise immunity. So you have to have a number of different techniques to manage that. Also, and then just as we go up in complexity with just in general interface and complex IP, you also have to deal with the quantization effect that we talked about before. You have to deal with heat like we're talking about before. You're talking about new rules for EM and IR. You're talking about very, very complex DRC rules that you have to come into effect. One of the other things I didn't mention but is an important characteristic is body biasing, which has been a design technique we've all used for years. And planar, with FinFET, the channel is elevating. Effectively, there's no doping, so that classic design technique really goes away, which again really calls for IP providers designing in FinFET to really look at fundamentally new architectures to deal with all these many challenges. So really, if I summarize this section here of the conversation about designing at FinFET, there's really, really good news. The really good news is that the burden falls on the foundries and the IP providers, and for the SoC designers, it's almost, not quite of course, because they have to deal with the same level of complexity and DRC rules and so forth, but it's almost business as usual. But the burden does fall on us as an industry to really take into account these new unique challenges that FinFET brings to us and really have excellent solutions here. And that really requires, as I said, a fundamental rethinking of architectures for essentially all of the IP that we have at Synopsys going into FinFET. We've really had to fundamentally redesign the base architectures to take advantage of FinFET as well as to compensate for a lot of these effects that we've talked about. But the race is on. I wanted to conclude this session with this portion of the presentation by really just saying the race is on. We're already designing at 10 nanometer in multiple foundries right now. There's absolutely no slowdown in the adoption of FinFET technologies, and in fact, quite the opposite. We're actually seeing 10 nanometer FinFET accelerate as our lead customers are going there and our foundry partners are going there. But now I want to talk about the second half of the world being bifurcating, IoT, automotive, other things, adding a lot more impetus to the established nodes. So one of the things that I very much agree with Tony in his presentation is that the Internet of Things, many types of things, I don't particularly like the term Internet of Things either because it is so complex, everything from sensors to servers, but this is some interesting data from Gartner DataQuest, as Tony was saying, pick your volume number. You can pick any number from 10 billion to 50 billion units. The forecasts are all over the place, but there's going to be a lot of innovation, and this is a very exciting time for us as IP providers and as a semiconductor industry, because I really do think that IoT is going to create a lot of very interesting new technologies. I was reading about a couple of interesting applications, like for those of you who may have young children, infants, there's now smart blankets that are coming out, blankets with sensors that will monitor your baby's heartbeat and transmit that to your cell phone so you can lie comfortably in your bed at night making sure your baby's safe or sound. Or another really interesting application that I thought of or heard about is smart slippers. You might say, why in the universe would anyone need intelligence built into a slipper? And for a person like you or I in this audience, you probably don't need that. But the world's population is becoming older, and as a person who has an 89-year-old mother, a fall is a big deal, a big concern. If you have sensors into your slippers, you can actually get an alert if your mother or your grandmother has fallen and may need some help. So there are, these are just two examples of some tremendous innovation that is happening right now in the industry that is driven by this ubiquitous connectivity. And I think it's a really exciting time for our industry as a result of that. So when we look at IoT from a Synopsys perspective, I'm going to mostly focus on the edge devices, but as Tony was saying, there is what's increasingly being called as the fog, different ways to aggregate all this data stream and doing it in an intelligent way, and then of course move that into the cloud, into the data centers. But primarily what I'm going to be focusing on here is I'm going to really be focusing on wearables, and I'm also somebody who likes to, like most of us probably, I'm a high-tech gadget guy, so one of the things I wanted to do in this presentation is actually model it. So I have a Fitbit here, which I wear all the time, and depressingly here it's telling me that I have 8,979 steps to go to hit my 10,000 goal, and this particular a fitness band happens to come from Garmin. It's called a Vivotech. And I don't know if you can see it, but there's a big red bar across the top of my band here, which says, that big red bar says, John, you have been sitting down for over an hour now. It's time to get up and get moving around. So it provides you a little bit of feedback as well and some motivation. But one of the things that is one of the reasons why I picked this particular device is because the battery in it lasts actually a year. And okay, so the screen's not backlit here, and it has many other things that compensate for having such a long battery. But In many of today's IoT devices, the battery life is simply just not acceptable. You're seeing the first generation of smartwatches needing to be charged every day. That simply is not going to be acceptable as we move forward into this brave new world of IoT. You're not going to want to, charge your slippers or your baby's blankets, like I mentioned before, twice a day. Right, that's not very practical use mechanism. So I think that while you're seeing here today some of the early incarnations, there is just so much work to be done in this area. And we as an IP industry and as a semiconductor industry have so much value that we can provide in taking power out of the devices and lowering the voltages and then coming up with new innovative architectures just in general to minimize power. But it's not just in the world of semiconductor. What I'm actually going to talk about in the next couple slides is some innovation that's happening in the world of power management as well. So first of all, the holy grail, I think, of all wearable devices is to be self-powered. And some of you may think, well, maybe that's a pipe dream, but it really isn't. So this is some interesting data here that you as a human being are actually a tremendous source of energy. So just, your body heat coming out is as much as 5 watts of body heat is being generated a day. Breathing, 1 watt a day. Things like when you're walking, 67 watts a day. Things like swinging your arm around, 60 watts. So, you as a human machine here can generate a lot of energy. And so the question is really, how can we tap into that energy that you naturally do to power some of these next generation of IoT devices? And so these are just some other things. In addition to the body, you're seeing indoor and outdoor lighting. You're seeing various energy from machines and so forth that can generate a fairly significant amount of energy. And so I think the challenge for our industry, one of the challenges for our industry is going to be, how do we harvest this? If you can just harvest even a small percentage of this, as little as 10% of the energy coming out of a human body or out of sunlight indoors, you can actually develop and power a whole new range of interesting applications. So along those lines, the era of batteries may be certainly not coming to an end. That would be way too bold a prediction and not true. But there are some new techniques that you may or may not heard of that are being actively researched that over the next 3 to 5 years, I think you're actually going to start to see them become mainstream. So the first is what's called a micro battery. And this is really being the primary research of this is the University of Illinois at Urbana campus. And so this is using a brand new type of material where you can capture and store as much as 100 milliwatt hours per centimeter squared, so centimeter cubed, I should say. So this is a very efficient and very small form factor for capturing energy. And this will, one of the things I'm really excited about this in the next slide, which talks about supercapacitors, is that these new types of batteries, if you look at my little fitness band here, you can see how thick it is. And these new types of energy storage mechanisms are going to really create a whole different class of designs in terms of form factors that I think are also going to cause IoT, a lot of innovation in IoT and a lot of creativity and things. All of a sudden you're not going to have something which is probably a good inch thick on your wrist here. You can get something that's very thin and very unobtrusive, even potentially woven into your clothing as an example. So we really are at a place right now where it's a very, very interesting technology. You have the micro batteries. You also have these things called super capacitors, which are a lot of the research is being driven out of UCLA here, where you have 2.5 milliwatts, milliwatt hours per centimeter cube, so nowhere near as efficient as a micro battery, but also much smaller form factor and again much more flexible. So this is some very, very interesting and very innovative techniques that are coming in, not just in the design of the semiconductors, but also in the design of the whole IoT ecosystem. So with that, I wanted to just conclude my presentation here with a handful of slides about, I talked about how the market is bifurcating, about how there's no shortage and rush. There's a tremendous rush to 16 and 10 nanometer FinFET, as well as a resurgence in the established nodes. And whether you're going to the latest process node or whether you're looking at some of these innovative new processes on the established nodes, one of the things that is absolutely true as an IP supplier is that the basics still count. You still have to have a very high quality, broad portfolio of IP that our customers can trust on. One of the things that I like to say is that, you know, every chip that's being done today is like a Hollywood blockbuster movie. It's $100 million, $150 million, right? I mean, just like you hear about these big bombs in Hollywood where the movies that just don't quite make it, you know, these things are bet your company chips. And so our customers are absolutely depending on us as providers, and this is some data from a survey that we do at Synopsys where we surveyed almost 2,000 engineers and we asked them what's the most important thing that you're looking for in an IP provider, and you can see right at the very top, the lower bars are better, right at the very top, the most important thing is the quality of the IP, right? With these blockbuster chips, you just cannot afford to respin your chips. You know, you're also talking about the next couple of ones are IP technology leadership, having the right IP in the right nodes, you know, having a very broad portfolio, having high quality IP support. All these things are saying, from our customers, are saying that these are the most important things. But, you know, honestly, these are becoming the table stakes at the game. If you don't have a broad portfolio of IP that's high quality, that's well supported, you know, you have to start asking yourself, why are you even in the IP, you know, game? Because this is the table stakes. This is what it takes to play. But what we're saying at Synopsys is this is simply not sufficient, though. You know, as Tony was saying earlier, increasingly it's about integration costs, it's about verification, it's about software. So we're hearing from a lot of our customers that for every dollar that they spend in buying IP, they spend another dollar in integrating that IP into their SoCs. And, you know, software, when I go around and I talk to our customers around the world, they're spending anywhere between 35 and 60% of their budget designing SoCs is now on software, and it's not on the hardware. And they're all facing tremendous time to market pressures. You know, clearly that's a very, very important attribute. We talked about it earlier with regard to the Asia markets and how we could all learn from those market dynamics, but it's not just limited to that. If you miss a Christmas season with a new phone or a new game or a new fitness device or something, you really have missed an entire market window. So time to market is really critical. So while I mentioned from a table stakes perspective, you have to have a broad portfolio of high quality IP. That's not sufficient. You really need to address these challenges of integration, of verification, of software development, of successful functionality into the SoC of our customers. So we recently announced a few months ago an initiative that we call IP Accelerated. In other words, an initiative about accelerating the integration of IP into our clients' SoCs. And in addition to the broad portfolio of IP, it really has three major elements to it that I'm going to double click in. So the first is for all of our IP titles now, what we ship is an IP prototyping kit. So this is something which has a reference design of our IP. It has it ships with a complete embedded Linux PC so that you can quickly bring up your software. It comes with drivers and Linux all pre-installed on this embedded PC. A reference desire is there. It comes with a PHY daughter card. Everything that you need literally to bring up this IP instantaneously. I mean, if you're interested, you can actually see at our booth in here, you can see a prototyping kit that we have here. You can literally plug the components together, hit the on switch, and in literally 1 minute, you're sitting there at a Linux prompt, and you can start doing your job, which is not trying to assemble the IP, not trying to create this prototyping system, but doing your job, which is to look at the IP configuration, to be able to evaluate if that gives you the best system performance, and even more importantly, for you to start early development of your software. So you're seeing that all of our IP now is coming with these IP prototyping kits that we think are very, very important to get your design right functionally, but also, even more importantly, to get the software up and going. We also have created not just a physical implementation of the IP, but we've also taken for all of our IP and virtualized it in something we call a VDK, or a virtual development kit. And so this is our IP that has been virtualized and is now available for you to use in a typical PC environment to develop software. It comes with an ARM 64-bit reference design here, and as well as a model of our IP, which is completely configurable. So again, this is a way to jumpstart your IP. And the last major element that I wanted to talk about in this new IP Accelerated initiative is about more and more what we are seeing is that there is a tremendous demand for multi-protocol IP, and more importantly, as our customers are moving upstream, as they're moving more into architectures and ecosystem and software, they're starting to lose some of their expertise down at the lower level. So they're saying to us, please, Synopsys, don't just provide us with the IP, but also please provide us with the expertise so we can very, very quickly integrate that IP into our SoCs. We're experts in our SoC architecture. You're experts in the IP. Let's marry these two together. Let's create a unique, customized subsystem that exactly meets our needs, and let's get to market faster. And so this is something that we have both standard subsystems, like Tony was saying in his presentation, but also the ability to very quickly customize these subsystems as well to a unique architecture. So with that, the march is on. It's a very exciting time, to be in the industry right now. I think we're right at the cusp of very substantial innovation. And as IP providers, the table stakes are high quality, broad portfolio of IP, but I'll submit to you that that's not sufficient. We as an IP industry have to focus on subsystems, on managing the complexity, on software, on getting it right, and we have to help our customers do that to be successful. So thank you.